Good morning, everyone. My name is Matthew Lordson, and as was just mentioned, I will be discussing the inadvertent weather modification associated with wind farms. First, I'd like to start off with some acknowledgments. First to Brian Ansell for being my advisor for this research. I'd also like to thank Texas Tech University and the Atmospheric Science Group there, as well as the National Science Foundation for their funding of this research. So first, weather modification associated with wind farms. What exactly is going on here? Well, there have been many studies, both observational and modeling, of the local impacts that are being created by these wind farms. Some of the results that have come from those studies include the kinetic energy that is being removed from the local atmosphere and enhanced turbulence within the wakes downstream of individual wind turbines, as you can see in this image here. And there's also an increased surface roughness just due to the physical presence of the turbines in the field. So we know that there are many local impacts, but there aren't many studies that have shown what's going on non-locally. And unfortunately, it's quite difficult to do this research with observations. So that's why I am taking a modeling approach to determine what kind of non-local impacts are being caused by wind farms. And so there's a need to know what impacts are being caused by the wind farms on large spatial and temporal scales. So for this research, I'm using WRF version 3.5.1, and I'm investigating cases where cyclogenesis is occurring in the central United States. I'm doing this two-part using ensembles of both wind farm locations and wind farm sizes. And I'm utilizing the wind farm parameterization that is in WRF. And the virtual wind farm that is in the model includes turbines with a hub height of 100 meters, rotor diameter of 108 meters, and a turbine spacing of just over 5D, which is fairly standard in wind farms that are in the field today. And this model has a 10-kilometer grid spacing and is run for 96 hours. And I'd like to mention here in this image are the locations of the wind farms for the location ensemble that I will primarily be discussing today. And those wind farms are 300 by 300 kilometers in size. So this parameterization that is in WRF for wind farms, it imposes a momentum sink at the vertical levels that are within the turbine rotor layer. And it transfers kinetic energy into TKE as well as electricity, as is shown in this diagram here. And the atmospheric drag is based on the thrust coefficient that is on the modern commercial wind turbines that are in the field today. So you can see the thrust coefficient here, which is a function of the mean velocity of the wind. And this drag goes into electricity. Here's the power coefficient of the wind turbine, and as well as TKE, and this TKE coefficient is simply the difference between the thrust coefficient and the power coefficient of the turbine. So I'll be looking at the difference between the wind farm parameterization being on and off to look at the perturbations that are caused by the wind farm. The wind farm parameterization alters the moist physics in the model, which was discussed in the previous session by Brian Ansell and Christian Auert. So to kind of go away from looking at these possibly unrealistic perturbations that are being caused by the moist physics in the model, I'm looking at the cyclone perturbations that are caused by this wind farm. So this is analysis on a 500 by 500 kilometer box that is centered on the center of the cyclone. So the case that I'll be showing you today is the 26th through the 30th of April of this past year. As you can see there in this image, there's the sea level pressure is being shown here, and there is cyclogenesis that first occurs in northeastern Colorado, and the cyclone deepens as it moves into Nebraska, and then at the end of the forecast, the cyclone is positioned in Iowa. So this first animation here is the pressure perturbation caused by the wind farm here in central Kansas. And as you saw at the very beginning of of the forecast, the local impacts are first seen, and then the perturbations within the wind farm are quickly moved downstream, and the perturbations grow upscale quite quickly and are ingested into the larger synoptic scale flow. And also near the beginning of this animation, as we'll see here soon, there were the perturbations that were off of the eastern coast of the United States, as you can see right there, and those are the more unrealistic perturbations that are being caused by the moist physics within the model. Just timing change between the control run and the wind farm run with formation of rainfall, and then that also creates perturbations with pressure and temperature, etc. So here is a time series plot of the minimum sea level pressure within the cyclone. And I like to point out that the x-axis here is the forecast hour. And so the cyclone wasn't evident until hour 21 of this forecast, so that's why the lines first appear there. And so we can see that most of these wind farms are actually decreasing the intensity of the cyclone here, as evident by the increased pressure within the cyclone. And one thing that stands out pretty evidently is wind farm member 6. And that was the location that was just shown in the animation in central Kansas. And this wind farm was located close to the area of cyclogenesis. And you can see here in this image that throughout the entire forecast, this wind farm member seems to be producing a larger perturbation than the rest of the ensemble members. And as I said, that this wind farm is decreasing the intensity of the wind farm, or of the cyclone, excuse me. But you can see evident between hours 72 and 84, wind farm member 9 actually increases the intensity of the cyclone. And this was interesting because at this point the cyclone was mature, and it was actually moving through this wind farm when between hours 72 and 84, when we see an increase in the intensity of the cyclone. Here is just I'll quickly show this plot as the maximum 10-meter wind speed perturbation caused by the ensemble members. And one thing that I'd like to point out are these two large spikes centered around forecast hour 72. There are many members where the maximum wind speed within the cyclone is decreased and then quickly increased. So that is telling us that the wind farms are simply altering the timing of this high wind speed event that was recorded within the cyclone. And here are the accumulated precipitation perturbations caused by the wind farm. And since this is a difference plot between the wind farm members and the control run, a positive slope indicates that there is more rainfall occurring within the cyclone with the wind farm present as opposed to the control run, and the opposite is true for a negative slope. There's more precipitation occurring within the cyclone without the wind farm when the lines have the negative slope there. So you can see that in this instance here with the wind farm 8 having quite a large increased precipitation that drops off quite quickly, just again due to the timing of this rainfall event between the wind farm member and the control run. And I'd also like to note that at the end of this forecast there are 5 members that have an increased precipitation within the cyclone, and 5 members have decreased precipitation that was occurred over the cyclone. So I'll quickly go over these next 2 plots, just showing the maximum and then minimum temperature that has occurred within the cyclone. You can see this wind farm member 6 is again coming out having greater perturbations as opposed to all the other members. That's the dark gold color there. And You can see, again, the wind farm number 6 has a spike in this minimum 2-meter temperatures. And so that's indicating that this wind farm that's located close to the area of cyclogenesis is having quite a large impact on the cyclone itself. And so I'll show this plot here. I also looked at an ensemble of wind farm sizes, which is shown in this larger image here. And the size ensemble is located over the area of wind farm number 6, which was in central Kansas. The purple line in this image here corresponds to the original size of the wind farm that was shown earlier in this plot, which was that goldish color. And I also have 8 other smaller wind farms that are located in the same area. And you can see with a decreasing size of wind farms, there is also a decrease to the perturbation that is being caused by the wind farm. But there are instances when smaller wind farms are actually causing a larger perturbation than the larger wind farms themselves. So to conclude, wind farms, as seen here, have a non-negligible impact on the non-local weather. And cyclones are generally being weakened by wind farms in the field today. And there are larger perturbations that are being observed when the wind farm is located near the area of cyclogenesis, as opposed to wind farms that are located farther away. So with that, I'd like to thank you for your attention and take any questions.
Thank you very much. So we have some time for question and comments. Yes.
The wind farm mentioned that actually strengthens cyclone. Could you propose a physical mechanism of why that would be?
Yeah, that is quite interesting. The question was the wind farm that actually increased the intensity of the cyclone and why that is. So here's that image that you're discussing. So this the cyclone at this stage was starting to weaken in intensity, and it appears that when the cyclone was moving through the wind farm, that it did not weaken as much as what it had in the control run. And why that is, it's very very interesting. I need to do more research into the specifics of what exactly is going on here, but unfortunately I don't quite have an answer for you today.
Any more question or comment?
So in the previous session, Brian talked about numerical artifacts.
Right.
Do you think any of this is impacted by that?
I'm sure it is, because there, of course, is precipitation that's occurring within the cyclone. So when you have the moist physics within the model that's being altered, you will be seeing some of that within these results here. That's just focused on the cyclone. However, I, tried to limit those effects as much as possible by, just looking at the smaller area instead of the entire domain. And unfortunately, previous research hasn't really touched on these impacts of the moist physics within the model. So that's something that needs to be looked into more.
I think there's a number of people in the audience who have heard the message, and we'll start looking into it.
Any more questions?
Yeah.
All of this was offshore. What about the farms offshore? Would you expect more results?
Yeah, so the question was results, how they could be different between onshore and offshore wind farms. I would guess that there would probably be a difference between onshore and offshore wind farms, because wind farms offshore are operating in a different environment than onshore. You have the marine layer and and your boundary layer has is different over the ocean than what it is over land, and you have surface roughness over land, and over sea it's much smaller, and so when you put a wind farm offshore, that increased surface roughness is much greater than what it is onshore, and so there are likely larger impacts offshore than onshore.
Okay, one more question.
One of your conclusions shows that cyclone is weakening.
Yes.
You specify or look into, in a quantitative way, how much is that?
Yes, so the question is, one of the conclusions was that cyclones are being weakened, and have I quantified that yet? Unfortunately, no, I haven't. These ensemble runs are quite recent, so I need to just run more and more cases and then get a more quantifiable number of how much these cyclones are being weakened by the wind farms.
Okay, so we have to move on to
All right.
the next topic.
Thank you.
Okay.